Hello world, welcome to Decoded. So I'm super excited to dive back into our little adventure of rescuing a corrupted PDF file. If you've been following along, you know that in the previous video we did some serious detective work and managed to fix the character mapping, the infamous Cmap inside our PDF file, and we got a lot of characters to show up properly again, which was a big win for us. But the plot twist still remained. We had some sneaky glyphs that were just fancy shapes representing characters that were plain hard to get. And they simply did not map to anything because all we had for them were their outlines. We could only draw them. So today we are trying to come up with the clever way to turn this PNG drawing of these glyphs into actual Unicode characters that a computer can understand and display properly. So we have a juicy problem in our hands with these corrupted PDFs and unmapped glyphs, and I'm pumped to brainstorm some solutions with you because this is my playground. Now, if you're a data scientist or data engineer like me, you know that these weird quirky challenges like this pop up at work all the time, and solving them feels kind of nice. So at first glance, you might think, hey, this sounds like a job for OCR, right? The optical character recognition, where computer looks at an image and figures out the text and stuff. But it turns out it's not that simple. See, we tried using popular tools like Python Tesseract, which is usually the go-to for OCR stuff, but it totally flopped, especially when dealing with glyphs from Eastern languages like Persians or Indians. Those pre-trained models just threw their hands up and say, no, I do not get it. So relying on an off-the-shelf OCR would be a big fat fail. Trust me on that one. Now, we could go down the road of building our own OCR model from scratch, or we can tweak and fine-tune an existing one to recognize these tricky glyphs. But as much as it sounds cool, both of these options they're like signing up for a marathon. They take a ton of time, effort, and resources. We're talking endless hours of training and data preparation and just burning through computing power. And let's be real, just most of us do not have that kind of time or budget just sitting around. So let's think outside the box for a minute. What other options do we have? What if we treat this not just as a text recognition problem, but as an image classification problem or image similarity search problem? Picture this. Instead of teaching a computer how to read, we teach it to match shapes. Like, hey, does this doodle looks like a character you have seen before? If we frame it this way, we can tap into some awesome deep learning tricks that are fast and cheap and super efficient. You know, we do not need to reinvent the wheel, right? So instead of forcing an OCR tool to slog through this mess inefficiently, we are taking a different approach. We are treating each of these characters as their own mission, a mini job to resolve, like puzzle where every piece needs to be figured out before we can see the big picture. And by focusing on one character at a time, we can be super precise and make sure nothing slips through. And besides that, if you have seen my previous part of this video, you would know that in case you want to repair, here is my repair part. In case you want to repair a PDF, you need to fix the mapping between the glyph index, here it is, the glyph index as an integer turns into hexadecimal, corresponding to the character base 16 numerical value turned into hexadecimal also. And we must deal with these unmapped glyphs one at a time anyways. So why not pass each one individually to our model? Okay, so here's the scoop. I went all out and created a huge data set of glyphs representing Persian and Latin characters and numbers, and I pulled these shapes from 200 different TrueType fonts, and I have built a giant sketchbook full of every way you could draw each of these characters. And there it is. And because I'm such a nice guy, I have published this entire dataset on Hugging Face for anyone to use it, so you can experiment with it too. And you can find the link to this dataset below. Now, with this dataset in hand, I got to work testing out some machine learning models to see which one could best recognize these doodles as actual characters. I tried a few big names in the game, so I tried models like ResNet, VIT, YOLO, each with their own style of solving the problem of what character does this doodle represent. I put them through their pieces, training each model on my dataset to see who could match these glyphs with the highest accuracy. And guess what? Both VIT and YOLO came out neck to neck, and with the accuracy score of 96%, of course after a little tuning on my hyperparameters and cleaning my data samples. ResNet did okay, but it wasn't quite up to par with the other two. So after some deliberation, I decided to stick with my VIT model for this job because it's lighter on resource and there are a ton of great documentation out there on tweaking its hyperparameters and boosting its performance. But on the flip side, Ultralytics offers a fantastic module for working with YOLO and fine-tuning it, which is also super tempting. But for this video, just VIT is what we are inferencing from. So this is where our VIT model comes into clutch. Where is it? There it is, VIT glyph classifier, which loads my VIT model and takes an image and spits out the corresponding character based on the ID I have assigned to each character in my mapping. And I'm resolving the ID that is predicted, that has been predicted using this VIT image, to the corresponding character based on this CSV file, which I have created simply. And we trained it to look at each glyph individually, and we're basically teaching our computer to say, that's an A, that's a funky looking Z, that's a T, that's a K, things like this. So for a quick recap, we have found the unmapped characters in the previous video based on this condition right here. This is the condition that if it's met, we call it an unmapped glyphs, which meaning we do not have anything but the coordinations for that individual glyphs inside that individual font inside the PDF file, inside the very first page of our PDF file. So this is important to remember. So, and for the ones we had the corresponding character inside the Cmap, we just convert them into base 16 integer numerical value and turn them into hexadecimal and just simply add it to our Cmap Unicode mapping. And for the ones that we did not have anything, we just assign a default value of X. As you might remember, if we take these unmapped glyphs and try to extract them, we should just see X's. But this time we have a model to tell us what character this doodle represents, right? So if I go on and run this once more, it should create these Cmap Unicode mapping. Where is it? Yeah, Cmap Unicode mapping, and based on this creates the content that PDF takes as the to Unicode section of the stream, which stores the Cmap information inside itself, and inject it into our stream and update our PDF stream. So after updating each font individually inside my PDF stream and save the same document as the fix, which should overwrite the previous one, after doing its job, I think it's done. There are these unmapped glyphs that our model recognized. And look at the fixed version of it once more. We should see we have the corresponding characters for all of these unmapped glyphs, but still something is wrong. The first thing is the spacing info within these words, and the second thing is the orientation of the characters. So this is as far as we can get using our PDF font and the previous system that we invented to repair our PDF. There is no way to extract the spacing info and inject this spacing info for each of these blocks using these methods I have told you, I have showed you. And see, the content we are interested in, like the actual text you see on the page, often lives inside special characters called content streams. That the thing you are looking at here. These are basically a series of instructions that tells your PDF reader how to draw the page, like a receipt for rendering. Put this text here, draw the line there, and things like this. Now, within these content streams, text is often somehow organized into blocks or chunks. You might hear terms like TD and TJ blocks thrown around. Okay, let me break it down for you before we go any further. TD is an operator that basically says, hey, move the text position to this spot on the page. It's like setting the cursor before typing. And then there are TJ blocks, which is where the real meat exists. It's an operator that says, here's the actual text to display alongside with some spacing info. These TJ blocks are often where the actual characters or glyph references hide. And they're super important to extracting the raw content of the PDF, especially when things are corrupted like this in our case. And they help us navigate the PDF's internal map and pull the text we need from it, even if it's somehow buried. So how do we get our hands on these blocks? That's where our PDF miner, the new module I have added to this project, comes in. It's like a Swiss knife for PDFs. It lets you dive into the contents, blocks, layouts, and even structure of the document, and unlike the previous tool that give you just surface level, and text miner PDF miner can help us access the low-level content streams and parse operators like TD and TJ blocks. And it is perfect for our mission because we're not just reading PDF, we are somehow tearing it, dissecting it. Also, it might not always be the most straightforward tool to wrangle. For example, it has its own PDF font class, which is totally different from the font tools TT fonts class, which we have used to mess with the font files inside the previous chapter. And with all its powers, PDF Miner still strangles with the same old problem, that is figuring out unknown characters or glyphs inside the PDF, which is familiar to you. That's the same headache we are dealing with here. But since PDF Miner can solve these unknown glyphs on its own, we are going to force it to play with the custom custom system that we have just built here. So here's how we're going to do it. We are creating our own custom PDF device, basically the thing that processes and interprets the raw data in PDF. Then we are gonna build our own version of it, a tagging device that is tailored to our needs. Inside this custom PDF device, there is a special method called handle undefined or something like this, handle undefined characters, and that's like an alarm bell. It gets triggered every time PDF Miner stumbles across an unknown glyph, and then it cannot figure it out normally. It might just move on, but we are going to override this method to say, I have a better idea. When it hits an undefined characters, it passes us two key pieces of information, which is the character ID, CID, and the font object, which is of TrueType PDF font of PDF Miner, not TrueType font that we are familiar with, but they're essentially the same thing. It's still loadable using TrueType font if we convert it into bytes. Okay, and all we have to do is take the character ID, look up inside the font and figure out what shape or doodle it corresponds to, and draw it as an image using our method function that we have created up there, and pass that doodle straight into our custom model, and our VIT model spits out the corresponding class name or character, and you can use it to replace the unknown glyph and figure out the corresponding character. So I have my device, I have my extractor. Let me just show you what this system can spit out. If we look at here, we should see the structure that is giving us, the PDF Miner can give us. It's the spacing info that I have told you about inside the TD blocks, which shows us the positions, the x1, x0, x1, y0, y1. It represents a box that this content lives inside our PDF. It's super useful if you want to extract custom parts from your PDF file based on a box you are considering from the PDF page. This is the distance from left, right, up, and bottom that gives us a standard box. So all this code is open sourced and available inside the decoded official GitHub repository. So if you look at here, I have 3 different repositories here. Here's the first one, this repo, the ML-Workbench, there is it. This repo is packed with some boilerplate code to train an image classification dataset. You got options to play with like transformers, YOLO, and torch vision, tesseract, and it's like starter kit for building your own glyph recognition model or any other classification task you might consider, just like what we did in my dataset, and you can trick and train your own content. Okay, so the main repository I want to represent here is an API containing the 2 steps I have represented inside my previous video and this video, all tailored together. This is an REST API with the cream on top, with a beautiful project structure. It simply repairs PDF, which should be familiar to you, find the unmapped glyphs, load it by TrueType font, and feed each unmapped glyphs into my VIT model and inject the corresponding character to my PDF. After you repair it, you return the same document here, and after that I am passing it into my PDF Miner, which I have just showed you. This is my PDF Miner, this is the device I have just showed you, this is the method I have replaced with to use my VIT model to draw each of these glyphs and map it into the corresponding character that it's predicting, based on of course the model's own knowledge. And if you zoom in the steps, it's okay. So in this step I am extracting the TJ blocks, and in this step I am simply normalizing the text based on a mapping I have created for myself here to simply each time you see a 1 or a number in Persian language, map it into the normalized version of it, which is the English numerical value of the same character. So normalizing it seems like a cool job because I am willing to extract the standard content from any type of PDF. I don't want any fancy Unicodes to appear inside my inside the list of my TJ blocks. So if I go ahead and run this API once more, I have even created an executor for the API and a config file to go ahead and load my model from an S3 object storage, which you can see in the resources, my config file. It is my object storage, and this is my bucket, and this is the model path I am expecting to load. Since I have already loaded it, it just comes up and run. And if I go ahead and send an example PDF, you should see some of the fonts inside this PDF are corrupted and unreadable by PDF Miner, which is okay because it just skips them and go ahead and try to extract the content blocks, the TJ blocks I have showed you, and after that normalizing them and gives you a standard structure of the chunks of text inside your PDF alongside with the positions of that box inside the text. It is super useful, and all of this happens seamlessly through the API. You can upload the PDF and you get back a JSON with the extracted and repaired content. And I told you I have published this repo, so you can check and use the models I have already created, and feel free to test it and with your own PDFs and see how it handles those tricky corrupted files and PDFs and content streams inside it. And actually I went much further than just basic extraction. I've developed a system that identifies specific boxes within a PDF page using coordinations, the x1, x2, y1, y2 I just showed you, and search for the text. For example, I'm looking for a field called field name at position blah blah blah, like this, and the system calculates the overlap to find the closest TJ blocks and then performs a small transformation on the match text and returning a dictionary of the field key and the corresponding text chunk that it finds inside the PDF. That's pretty sick. And also, if you got ideas on how to make this API even better or want to share how it worked for you, drop it in the comment. I'm all ears. And finally, I have a third repo containing code that does an image search. Let me just close that. There is it. It does an image search on our GlyphDataset instead of pure classification. It uses image similarity search to find the closest match for a glyph and figure out the corresponding character. It's a different approach. It's a different angle to solve the same problem, and it might just be the trick you need for your project. So I published all three of these repositories, and you can grab them, mess around with them, and make them your own, whatever. Okay, I think we covered some serious cool grounds today in fixing our corrupted PDF. We introduced PDF Miner module and dig deep into raw structure of our PDF file. And we cooked up a clever plan to create a custom PDF device that teams up with our glyph recognition system by overwriting that handle undefined characters and the stuff. And I'm gonna wrap these things up here for now, but although we got plenty more to explore as we keep tracking these PDF puzzle, if you want to continue on this journey, I suggest you head over the GitHub repo of Decoded, and I've put the link in the description below, and play around with it and tweak it and let me know how it works for you. And if if you got questions or crazy ideas about PDF hacking, drop them in the comments. I'm all ears. And if you enjoyed